So yeah, thanks for inviting me. So when I accepted the invitation, at first I thought I would give a talk just about black holes. But then thinking back to my previous visit to Chicago, I thought it was quite beautiful how cohesive the high energy and condensed matter audience was. So I thought I would give a talk that was partly about black holes and then partly about chiral field theories, which I think would probably resonate with everyone a little more. But in the end, I decided to expand the part on chiral field theories, and it's probably more coherent to actually just talk about this. So okay, so there are many ways to motivate chiral field theories. And well, I will give some motivations that will feature sort of in the later part of my talk. So I'm going to begin with ADS CFT, which is our best understood non-perturbative formulation of quantum gravity. So you put it in ADS, and the highly non-trivial conjecture is that it can be completed by a CFT on the boundary. And there's a very rich dictionary in this correspondence. Arguably, the simplest unitary setting of ADS CFT is the purported duality between 3D gravity and 2D CFT. And the very special thing about this dimension is that 3D Einstein-Hilbert action is super renormalizable. So it seems possible that a UV complete consistent theory of 3D gravity exists. Namely, you don't need extra compact dimensions, as is usually the case in other string theoretic constructions. Well, we don't really have a non-perturbative formulation of quantum gravity, even if it's in ADS3. So it is often, gravity in ADS3 is often studied through its equivalence to 2D CFTs. And I want to point out that there's a very nice paper recently that makes significant progress on sort of a formulation of 3D gravity. Now, another motivation is sort of more on the methods aspect. So like in recent years, the Bootstrap program, which constrains theories by mere consistency and symmetries, has had a lot of success, in both in just the CFT context and also in the holographic context. While this universal approach is very powerful at, yes?
Sorry, so I was just trying to understand in what sense the previous slide was a motivation. This is about the boundary gravitons being some sort of chiral theory, or?
I will get to it. Here I'm just, this is very broad motivation. Yeah, I will get to it. Okay, so here, yeah, so Bootstrap, while being very powerful at producing rigorous bounds, it's very limited for instance, studying theories inside the bounds, which in fact is the vast majority of theories. And so to solve certain problems in both the CFT context and by extension gravity, we need some new approaches. So basically this talk is about trying to formulate new constraints, exact constraints on CFTs, which has implications on gravity that transcend the common Bootstrap and symmetry methods. And the focus of this talk is about the simplest type of CFT, which is 2D CFT. And not only it's 2D, but we're considering chiral CFTs. Now, the word chiral can have many different meanings. So let me make precise what I mean by chiral CFTs. So let's begin from just the free scalar field in 2D. So here's a very simple Lagrangian. And the fact that the equations of motion has this factorized form, it means that the kinematics is factorized into left and right degrees of freedom. However, even though the kinematics is factorized, the full theory is not factorized. Now, this slide is, the previous slide was about, this is the free scalar example, but the kinematic factorization is a feature of all 2D CFTs. Because of this factorization, it makes sense to count left and right degrees of freedom separately. And so we can define two notions of central charges, C left and C right. They're normalized, usually normalized in a way that for this free scalar field, they're both one. Just like in the free scalar example, the full theory, the full 2D CFT is generically not factorized. So this means that basically the left kinematic representations and the right kinematic representations, not every pair is actually paired up and appear in the theory as a local operator or as part of the Hilbert space, but there are constraints. However, there's a very special class of 2D CFTs where the full theory actually is factorized into left and right. And these are known, sometimes they're called chiral CFTs. And that's the sense I'm using this word in this talk. And chiral CFTs can be further divided into sort of bosonic versus fermionic ones. Depending on whether, when you define them on a space-time manifold, whether you need or whether you need a spin structure or not. By consistency, the central charge of a bosonic chiral CFT has to be a multiple of 8. And that of a fermionic chiral CFT has to be either an integer or a half integer. What we'll feature later is a stronger notion of bosonic chiral CFT, which actually requires the central charge to be a multiple of not just 8, but 24, so that there's no global gravitational anomaly. And this notion of chiral CFT, this is often called holomorphic CFTs. And this notion is often motivated sort of in the high energy context. So are there any questions at this point? So far I'm just defining what I mean by a chiral CFT, clarifying some notions. And okay, so now here are sort of the perspectives on chiral CFT that I want to discuss today. So the first point is about replica symmetry and some implications on sort of the realizations of chiral theories on the lattice. Next, I want to introduce a rather novel constraint on chiral CFTs by way of quantum bordism, or a version of it known as topological modular forms. So it's going to put constraints on, it's going to put constraints on all CFTs, all chiral CFTs, that allows us to make progress on their classification. And it will also rule out a longstanding conjecture of Witten's. Lastly, I will discuss the classification of fermionic chiral CFTs. So let's begin with replica symmetry. So a very basic operation on physical systems is essentially to take their product, also known as stacking. In the product theory, the permutation of replicas becomes a global symmetry. In the lattice framework, it would be an on-site symmetry. And sometimes we want to gauge this replica symmetry for several reasons. So first, you might just think, a product of decoupled theories might sound a little boring. So one way to couple them together is essentially to gauge this replica symmetry. Then in the holographic context, so this gauging procedure essentially reduces the degeneracy of light states. And this makes it possible for the CFT to be dual to a weakly coupled bulk theory. So, there are different reasons to consider gauging the replica symmetry, which begs the question, can we always gauge it? The answer is yes, if the gravitational, well, so let me talk about 2D first. So the answer is yes, if the gravitational anomaly vanishes. So in particular, if you have a non-chiral theory, then yes, you can always gauge the replica symmetry. But if you have a chiral theory, either chiral CFT or more generally a theory that has a global gravitational anomaly, then not always. So the condition is that the replica symmetry of a chiral CFT is fully non-anomalous if and only if C is a multiple of 12. So here, by fully non-anomalous, I meant that the full symmetric group has no pure anomaly. So in fact, so actually, if C is a multiple of 12 but not 24, there is a mixed anomaly between -1 to the F and the permutation symmetry. So maybe I shouldn't really use the word, I shouldn't really say fully non-anomalous. But anyway, the message is that the replica symmetry can be anomalous for chiral theories.
Can I make sure I understand what you mean? So you mean take n copies of the theory and mod by Sn, the overflow by Sn?
Yes.
Okay.
Or any subgroup of, or some subgroup of Sn.
Also, so is the condition, so here is the condition for a non-anomalous overflow different from the past conditions because it's chiral? Like going back to the whatever early days of overfolding. I mean, it was basically level
It's the same.
It's the same. Okay.
It's the same condition. Yeah. So yeah, I'll describe how to like very easily see this anomaly by like essentially a one-line derivation or two-line derivation. But first, let me say that this has been established rigorously, so mathematically. And then just in a recent paper for some other reason, we encountered this, and in an appendix, we also describe how to see this very easily in physics. So let me sketch for you the derivation. So we know that anomalies can be detected by the spin content in the Hilbert space twisted by the symmetry. So for instance, if you have in 2D, if you have a Zn symmetry with k units of the anomaly, then the spin of operators in this twisted Hilbert space has to belong to the set that's on the slide. So basically the spin mod 1 over n is quantized in a way that depends on the anomaly k and nothing else. So to tell whether the replica symmetry is anomalous or not, we just have to compute the spin when you have like multiple copies of a theory and you just twist by this permutation symmetry. So consider a cyclic permutation pi of n replicas of a bosonic chiral CFT X, where a single copy X has central charge C. So n copies has central charge NC. And let's just compute its torus partition function twisted by this cyclic permutation symmetry. Okay, because once you compute this partition function, then in the trace definition of it, we can basically read off the spin content. So how do we compute this? Basically, we start with n copies of the torus. So think of each replica of the theory living on one torus each, and we insert this symmetry line, which is essentially a branch cut that takes you from one copy to the next, and then to the next, and so on and so forth. So I've drawn some pictures on the right. So you can see here there are n tori, and if you cross this blue branch cut, say from the left, then you emerge on the next sheet on the right, and then if you so on and so forth. You can very easily convince yourself that this branch covering of a single torus, well, of these tori is nothing but just another torus that has the spatial length enlarged by n times. So in other words, the modulus of the torus is divided by n. And that's basically what the formula on the left is saying here. So it's extremely trivial derivation. And once you have this formula, you can just read off what the spin is. And by comparing with this formula on the bottom, you can also read off what k is. So this is a formula that works for bosonic CFTs. And so k is in fact an integer, and it's easy to see this. So c has to be a multiple of 8. So the denominator can at most be 3. But then you see this expression in terms of n is basically the product of 3 consecutive integers. So one of them has to be divisible by 3. So k is an integer. There's a similar derivation of this for fermionic theories, but I'm not going to repeat that exercise here. But if you're interested, you can do it yourself, or you can also just look at our appendix. So just to give you some simple examples, just take the 2D chiral E8 WZW model, which has central charge 8. The exchange of 2 copies is non-anomalous, but if you try to take 3 copies, then the cyclic permutation is in fact anomalous. And I should point out that this anomaly seems to have intimate connections with the sort of the generalized Hecke operators that Jeff and students were studying a few years ago. So what's the connection? So think about symmetric product orbifolds. It's known that the partition function of a symmetric product orbifold has a formula. You can write it in terms of exponential of some Hecke operators. And for the multiplier system implied by this amount of anomalies, C equals 8, the second Hecke operator is well defined, but the third Hecke operator is not. And I think it's basically reflecting the fact that when the cyclic permutation of 3 copies is anomalous. But that's just a side comment. So another example, so for fermionic chiral CFTs, it turns out that if you just take a single chiral fermion, which has central charge 1/2, then the exchange of 2 copies is already anomalous. And so what does this tell us? Well, as I mentioned before, if you have a lattice, then the exchange symmetry, or more generally, the replica symmetry, it's an on-site symmetry. So it has to be non-anomalous. And combining this statement with the fact that the exchange of 2 replicas of a chiral fermion is anomalous, we infer that a chiral fermion cannot be realized on a 2D lattice. So in this way, the replica anomaly offers a robust argument, a very clean and robust argument for sort of the 2D version of Nielsen Ninomiya. Now, so far this discussion, this talk is mostly about chiral CFTs in the sense of only having, say, left-moving degrees of freedom. But this statement about replica anomaly is general for QFTs, 2D QFTs with global gravitational anomaly. So one just has to replace the central charge by sort of the amount of global gravitational anomaly the theory has. It is, at least to me, it is highly conceivable that there's a general connection between global gravitational anomaly and replica anomaly that persists also in higher dimensions. So I think it's natural to conjecture that in 6D, where the sort of the representation theory of the spin group share many similar features with 2D, that a Majorana-Weil fermion also has the replica anomaly. And if this is true, it would also imply that a 6D chiral fermion cannot be realized on the lattice. The most classic version of Nielsen Ninomiya is, of course, in 4D. But here, the notion of chirality is a little more subtle because you have to define it in reference to another global or gauge symmetry, such as a U1. But if you imagine that, say, n Weil fermions have a mixed replica anomaly between the permutation Sn and this reference U1, then it would also imply a version of Nielsen Ninomiya. It would be a somewhat weaker statement, but yeah, there will be a version of the statement.
Sorry, could you
So
I'm just not familiar with this Nielsen Ninomiya. Could you just roughly explain what that is?
oh, it's just about it's just a statement that you cannot realize chiral fermions on the lattice.
Thank you.
Yeah, but ignore was the argument clear that because in the continuum description the symmetry is anomalous, whereas in the lattice description it's non-anomalous, and therefore you should not be able to realize this continuum theory on the lattice.
Yeah.
Okay. So for higher dimensions, well, there is sort of
How do
a
you
very
know that on the-
well-defined.
Ying, can I ask a question? How do you know that on the lattice it would have to be an on-site symmetry? Maybe the replicas are shifted by a site.
But you can always define it to be on-site, no?
Well,
I mean, there's
you're
always
saying,
a way to define it.
you're saying that there exists some on-site symmetry that you're ruling out, but I feel like you're sort of assuming the conclusion. I mean, you know, the one can realize anomalous symmetries on the lattice if they're not on site. So how do you
Yes.
know that there's not some very creative way of putting multiple chiral fermions on the lattice where the degrees of freedom are offset? Who says that I have to stack them literally on the lattice? It just has to be stacked in the continuum.
So maybe here I don't know what the most general definition of stacking is. Here I'm just imagining that you're just, you just have multiple copies of the single copy, the degrees of freedom on a
Right,
single site.
I'm just complaining. I'm just pointing out that there's a little bit of an assumption there, in that
Okay.
you are what we know is that what we want to achieve in the continuum is the naive stacking, but what that lifts to in the UV on the lattice, we're not yet sure of. One possibility is that it lifts to just naive stacking of whatever lattice system you have, but it could lift to something more subtle.
Okay. So you're imagining some kind of staggered lattice where somehow you don't just repeat the same, on-site degrees of freedom on the same site.
Yeah,
Okay,
that's what
but,
I would imagine.
yeah.
Otherwise, you definitely can't realize any anomaly.
Okay, well, I'm not familiar with like all the possible ways of stacking, so maybe I'll just say that this tells you that you cannot realize a chiral fermion with the replica symmetry being on site. But let me wait. But I feel like the logic, I don't know. So let's say I can realize a single chiral fermion on the lattice. Nothing forbids me from defining, let me just stack it in the naive way, right? Then I will get a contradiction, no? Like, you're telling me that there are different ways to stack it, but I can always choose to stack it the naive way, right? That's always viable. I'm just trying to prove that a single chiral fermion cannot be realized on the lattice. So I just assume the contrary. Suppose it can be. Let me take that lattice. Let me stack it the naive way. And then there seems to be a contradiction, right? Because then I do have an on-site replica anomaly. On-site replica symmetry that's non-anomalous. And I mean, if a single copy in the continuum limit becomes a continuum chiral fermion, like if you have, say, stack two copies, then I would think that, in the continuum limit, you would have.
But are you saying you don't need to make any assumption about what the UV symmetry is? Like, you don't need to make any assumption about how the symmetries emerge or anything like that? I'm trying to tease out what the assumptions are.
I'm not sure if I'm missing. I feel like the logic is robust, but at least I don't see what I'm missing, because I don't really. So the only symmetry I'm talking about is the replica symmetry. Okay, and the single, chiral fermion, I don't care about its symmetry at all. So I'm just assuming that, suppose you tell me that you can realize a chiral fermion on a lattice. I'm just taking your lattice realization and stacking it the naive way, right? There's nothing preventing me from just stacking it the naive way. And then I get a contradiction, right? Is there a loophole in that logic?
Well, I'm not sure. We should talk about it.
Okay.
Yeah, I feel like you might be assuming something about how the symmetries are emergent, but but it sounds interesting. I would like to talk more about it.
Okay. Thanks for the question. Yeah, we should talk. So, okay. So, barring potential logical subtleties, which I currently don't see, here. Well, okay. I'm not very fluent in all these like bordism calculations and analyzing the anomaly of a free fermion, but this potentially is it's a well-defined thing that one should be able to compute and determine whether the replica anomaly is there. And I just think it's interesting that it might be a way to give like a very clean version, clean argument about the realizability on the lattice. So that's essentially the first part of this talk. Okay, so now I'm going to talk about something still about chiral CFTs, but a little different. So let me give a motivation for this part of the talk. So, people have dreamed of classifying 2D CFTs, since the 80s. And it's an ambitious program that, there's always some non-trivial continued progress, but still it's quite limited in reference to, the whole zoo of 2D CFTs. Since factorization, since factorization is a tremendous simplification, one would imagine that if it is at all possible to classify 2D CFTs, then one should the simplest problem would be to classify chiral CFTs. Now, chiral CFTs for small central charges are essentially, they have been extensively studied in different contexts, but for example, in heterotic string theory, people have studied chiral CFTs at central charge 16 and I guess below. However, a rigorous classification was not attempted. So this is motivating sort of the third part of my talk. But before that, let's just talk about bosonic chiral CFTs. Bosonic chiral CFTs at central charge 24, they were famously, conjectured by Schoelekens and more recently proven rigorously by mathematicians. But beyond 24, there has been very little progress. Now, relatedly, so in this context, basically Witten had conjectured the existence of a family of chiral CFTs with so it's a family with increasing central charge, all divisible by 24. So C equals 24K, based on some observations about 3D gravity. So this conjecture was mainly motivated by ADS CFT. One of the nice observations about this conjecture is that the first case, K equals 1, is realized. So there is one very nice CFT called the monster CFT that satisfies the nice properties that Witten wanted for there to be a nice 3D pure gravity dual. Since then, people have tried quite hard to construct examples at C greater than 24, so K greater than 1, but failed. People have also tried, say, using Bootstrap and other ways to disprove the conjecture, but there's also been essentially no progress. So this problem has been essentially in limbo for like 15 years.
Can I ask about that? So the conjecture is based on the desire to have a theory of pure gravity, or there was some additional evidence that these theories should exist?
No, so in this paper by Witten sort of laid down it's not a fully complete quantum definition of 3D pure gravity, but he wrote down some like a Lagrangian and discussed some nice properties that such a theory would have, and their reflections on the dual 2D CFT. So basically, these would have to be chiral CFTs with a gap that grows with K. Yes.
Yeah, okay. So something that includes just BTZ black holes and nothing more, or?
Yes, that's right. This is about pure, yeah, I didn't write down the specifics in the slide, but it's about pure gravity. It's about like the purest gravity where you exclude all the light states as long as it's consistent with modular invariance. So you only have, the Virasoro descendants of the vacuum and then the BTC, and then, above it.
Sorry, isn't that, I thought, if I remember correctly, that even then, the heavy states did not really match perfectly with BTZ black holes. Like
that's right. That's right.
The chiral ones, the spinning.
Yes. So, okay, there's always been these problems about this proposal, but okay, so the original conjecture was motivated by gravity, and Witten already discussed all these issues in his paper. But we can just think of this conjecture as a pure a conjecture about chiral CFTs. Okay, and so I'm going to tell you some new constraints that has implications on this conjecture. Okay, so let me continue. All right, so what's the new insight or new tool here? I guess 2 years ago, Tachikawa and Yamashita presented an explanation of the consistency of heterotic string theory through a non-trivial connection between physics and an object known as topological modular forms, TMF. And let me warn you that TMF is not, topological is not a descriptor, but TMF is not a modular form. You should think of it as some different mathematical entity, although it has relations to modular forms. And so this connection will turn out to also be key to a non-trivial constraint on the classification of all chiral CFTs. And in particular, we're going to rule out this conjecture by Witten. And what I think is extremely interesting about this conjecture, about this, is that this connection, basically we have insurmountable evidence for the connection, but we don't have a physics derivation as of yet. So one could say that this connection sort of transcends what we currently know about quantum field theory. So what is this new constraint? So I'm going to present it for simplicity just in the context of bosonic chiral CFTs with central charge divisible by 24. So the partition function of such a CFT would look like this. The leading term would just be the vacuum, and the vacuum energy is dictated by the central charge. So you see it starts from K over T, and so on and so forth. Let's focus, so not on the ground state, but actually on the constant term, the constant piece of this partition function. Naively, this constant, could be anything, just any non-negative integer. Well, probably has to be positive because it also counts descendants of, say, the vacuum, etc. But naively, any positive integer that's consistent with the decomposition into Virasoro, positive decomposition to Virasoro characters, naively is consistent, right? However, it turns out that this highly non-trivial connection in the previous slide implies the following condition. If you take the K, which measures the central charge, and you multiply it by this constant term in the thermal partition function, the statement is that that product has to be divisible by 12. And as we know, quantization conditions in physics often come from anomalies, but there's no physical derivation or understanding of this anomaly so far. Well, okay, there's no sort of rigorous physical understanding of this anomaly so far. So currently the only explanation comes from just sort of this connection, and I am going to tell you. So I've told you that there's this thing called topological modular forms. I haven't really told you what it is. So that's what I hope to do in the next few slides. And I'm going to first give you sort of a cartoonish impression for why a mathematician would want to define such a thing. I will then try to give you a picture of what it is, beginning with sigma models, and then how it gives rise to this quantization condition. So here's the cartoonish description. So suppose one is given such an integer series like this, satisfying the non-trivial property that z at temperature T is the same as z at temperature roughly 1/T. So there's some kind of high-low temperature duality. A physicist will, if a physicist sees such a function, it would think that this is the partition function of a physical system, with this low-high temperature duality. Now, if you give this object to a mathematician, say Mike Hopkins, then what he saw was this thing called topological modular forms. I know this analogy is not very informative. What I'm saying is just that for us, for physicists, there's sort of a natural refinement from such a partition function into a full physical system. For a mathematician, there's also a natural refinement of such a function with these nice properties into a much richer, mathematical structure, and that structure is this TMF. So, sort of that's the. Okay, I'm going to be a little more. I'm going to say a little more later, but I want to point out that this connection between physics and math is basically this very non-trivial conjecture that the physicist and the topologist actually see the same thing. So you start from this partition function. The statement is that, yeah.
No, there was just a trivial comment. I don't want to, I'll ask later.
Okay. Yeah, so the conjecture is that the physicist and the topologist actually see the same thing in the sense that TMF provides an invariant, like an RG invariant, a complete invariant for physical systems satisfying certain assumptions. Now, so this is a conjecture in the 2D context, but we essentially believe that it's true. So there's a version of this connection in 1D quantum mechanics that is mathematically rigorous, and it's proven. For 2D, there's a lot of evidence, studied in all these contexts that makes one, it's hard to doubt the correctness of the statement, even though we don't have a physical derivation.
I'm still confused by what the statement is. What's the precise statement? So you, on the one hand, you have a physical system with a partition function. On the other hand, you have a topological modular form. And how are they meant to be related here? One is less data, presumably, than the other, right?
Good. Yes. So the statement essentially is, if you have consider 2D CFTs with minimal supersymmetry, and we think of not like the space of all CFTs, but we mod out by deformation classes that preserve the supersymmetry.
So 0, 1 or something in this case.
0, 1, yes. So 2D 0, 1 QFTs. And the deformation could be RG flows, but in principle, it could be just continuous deformations. And the statement is that once you mod out by the deformation, by deformations and speak only of the deformation class, then there's a one-to-one correspondence between deformation classes of 2D 0, 1 systems and classes in this TMF. That's the statement.
I see.
And it's conjectured to be a complete invariant. So the conjecture is that if two systems have the same TMF class, then there must exist a deformation that relate the two.
Sorry, can I ask about something that's confusing me here?
Mm-hmm.
You're saying that it's rigorously proven for quantum mechanics, but not rigorously proven for field theory. But I'm confused. Why isn't the quantum mechanics, the field theory case, just a special case of the quantum mechanics case? Are you, when you say one-to-one, are you assuming one-to-one with? Do you mean one-to-one with local theories in more than one dimension, or?
What is the quantum case here? I mean, what's the modular object you associate to the quantum case?
Oh, it's not. It's well, okay. So there, it's the the analog of TMF is KO theory. So real K theory.
So
and there, yeah. So think of it as a refinement of the Witten index. So as long as you have quantum mechanics, you can define the Witten index. Yeah. But sometimes, even when the Witten index vanishes, there's actually still some torsion valued invariant due to supersymmetry. That is that's an invariant under deformations. And the statement there is that classes in KO theory provide the complete description of such invariants. And then once you go to 2D, we're talking about, so our observables will be partition functions on a torus, which now, so this partition function already, even if we don't talk about like refinements, just the elliptic genus is already carries more information than just the index. And one can think of the TMF as a refinement of the elliptic genus, just like KO theory is a refinement of the Witten index.
So I'm sorry, I still didn't quite get the answer though. So is the issue that in 1 plus 1D, it's a function of the complex structure modulus rather than just the temperature? So I still don't understand why the 1 plus 1 case and higher are just special cases of the quantum mechanics case.
Yeah.
I mean, yes, it is a modular object in 1 plus 1, and it's just a single class in quantum mechanics. Aren't you?
There is an
assumption of locality.
So
that's what.
Yeah.
Okay.
Yeah,
I don't see where locality is playing a role.
Well,
I mean, there's modular objects.
Locality.
Which the position function?
The partition function. Yeah, he's saying that.
No, it's not. The position function is not a modular object. 2 plus 1.
He's saying
the twisted position function, right? Which here would be trivial in this case.
I don't think it's supposed to. I don't think it's supposed to be trivial. I mean, except for torsion.
Except for torsion. So it's only the torsion component that they're classifying. So the Witten index will refine down to something, and that's just a number at the end. And it's a refinement to that. It sounds like, unless I'm misunderstanding.
Yeah. So maybe let me first comment on why the locality would go into this, would affect things, because we're talking about deformation classes, right? So if you impose locality, then the deformations you can do in 0 plus 1D would be like a larger class than in 1 plus 1D. And that's why the deformation classes in 2D would be richer than 1D.
Good. So you are talking about when you say 1-to-1, you're talking about 1-to-1 with local theories and 1 plus 1.
Yeah. So all these statements, as far as I know, are made in should be understood in continuum quantum field theory. So even though I keep using the word quantum system, but there's some locality in there.
Okay, no, that's fine. I figured that was what you meant.
Mm-hmm.
So my only
And
other.
about your comment. Yeah,
No,
sorry,
go ahead.
Go ahead.
Go ahead.
Oh, I was just going to say this reduction. Yeah, you can reduce a 2D theory to 1D, and there is a map from TMF to KO. So
Good, okay.
so indeed, yeah. Sorry. So were you about to say something?
I have one other trivial comment about the last slide. If you could just go back for a second so it doesn't stop bugging me. Yeah, there's a little, I think you mean Z of t equals Z of 1 over 4 pi squared t. 4 pi squared is in the numerator when you're transforming the inverse. That's all.
Okay.
Yeah.
Okay. Thank you.
Sorry.
Thank you. Okay. So now I'm going to sort of I mentioned the word quantum bordism. So I'm just going to give you sort of an intuition for what this TMF is using this bordism language. So let me start from sigma models. So sigma models are QFTs with Lagrangians of this form. It looks like a free scalar field, except that you have a non-trivial metric, this capital G there, that sort of captures the information, the geometry of the target space. And of course, as we all know, these were invented in the 60s to describe pions and chiral symmetry breaking. Now, some deformations of this QFT, you can think of it as having a geometric origin. They correspond to geometric changes of the target space, namely of this capital G. However, I mean, the sigma model is a type of QFT, but of course there are non-sigma model QFTs. So you can imagine that there are deformations in the sense of QFT that is not geometric, that deviate from the sigma model picture. And one might as well call them quantum deformations. Now, let's stick to the geometric picture for now. So think about just sigma models. A natural set of geometric changes to allow are in fact bordisms. So this audience probably all know what it is, but let me just spend like 30 seconds to just define it. So two manifolds A and B are bordant if there exists a higher dimensional manifold with boundaries such that the boundary is sort of this disjoint union of A and B. So like on the right, I'm showing you that one circle is bored into two circles. And in fact, any numbers of circles, they're all bored into each other, without adding extra structure. And so this motivates a notion of bordism class. So all manifolds bordant that are bordant to each other are said to be in the same class. For sigma models, bordism classes are invariants of geometric deformations. These are deformations that make the QFT stay in the realm of sigma models. But if you can also deform away from the sigma model subspace. You deform through abstract QFTs, and then it sort of makes sense to speak of quantum bordism classes, which are invariant of the more general deformations that can take you leave the sigma model loci in the whole space of QFTs. So this is sort of the way to think about quantum bordism. And there are many different versions of quantum bordism. It's actually more commonly used in the KO context, in the quantum mechanics context. But the statement is that for 2D QFT with minimal supersymmetry, this connection between physics and TMF that I kept mentioning is the statement that this quantum bordism theory of this 2D QFT can be described by this thing called TMF. And if you're wondering, this TMF, just like KO theory, is a generalized cohomology theory. Okay, so are there questions about these two slides? So if not, yeah.
Okay, well, since you are letting us, are there non-geometric deformations in higher than 2 dimensions? Do sigma models in higher than 2 dimensions have non-geometric deformations?
Yeah, so higher than 2, it's tricky. So here I'm mostly focusing on 0, 1, and 2 dimensions. In higher
Okay.
dimensions, sigma models, these fields have they're dimensionful, right? So
Right, yeah, I see.
yes. So here, this discussion is, let's say at most 2. Let me restrict you at most 2D.
Okay.
Yeah, thanks for the comments.
Ying, I don't understand why supersymmetry is playing a role here. What is supersymmetry doing for this conjecture?
So, well, if you don't have supersymmetry, so okay, let me see. If you don't have supersymmetry, then it's hard to imagine what kind of invariant would be, right? Like, if you don't have supersymmetry, you have partition functions. If it's a fermionic theory, you have partition functions on, say, 4 spin structures, but none of them is a deformation invariant. Here, the role of the supersymmetry is so that there exists deformation invariants. So for example, if you have this amount of supersymmetry, the elliptic genus, which is the partition function on the non-bounding, the sometimes called Ramond spin structure, is a deformation invariant. And then this TMF is an upgrade of the elliptic genus that, after this upgrade, it's conjectured that there's a 1-to-1 correspondence between this TMF and the deformation classes of 2D QFT with this amount of supersymmetry.
But it just looks random. How do you know that there aren't more invariants?
It's a conjecture.
So there's no evidence? It's a conjecture? What's the evidence?
There's no counter evidence.
That's a good criterion.
It's a conjecture with lots of checks and no counter evidence.
Why did Stoltz and Teichner conjecture this?
I'm not really sure how the minds of mathematicians work. But yeah, I don't know. My very well, I feel like it's just because sort of these two sides are sort of a physical way of refining something like an elliptic genus versus a mathematical way of refining it. So it might be natural to conjecture that there is a correspondence. And I think a lot of the motivation was from the success in quantum mechanics that, in 1D, the analogous statement is actually true. So that would be my guess, but I don't really know what they were thinking.
Can I ask a refinement of Clay's question? I think that was Clay.
Mm-hmm.
Okay. For 0 + 1D, I can understand why a mathematician would conjecture it, because then it's just some statement about like operators, and mathematicians know what like operators are, right?
Yes.
But mathematicians don't know, or at least if they do, I would love to meet some, but I don't think they do know what local 1 + 1 dimensional quantum field theory is, or local quantum field theory at all. Even though they're mathematicians who, put quantum field theory in the title of their subject, but they don't think of it the way normal people do. Why would a mathematician conjecture anything about the space of deformations of 1 + 1 dimensional theories respecting locality, which they don't even know what that is?
So that excellent question. So they don't. So first, this is not a mathematically well-defined conjecture. I shouldn't say that. So they try to define in a mathematical axiomatic way what a 2D QFT means.
They do.
And they call it Euclidean field theory, but there are limitations. It's not clear that it's the same as the physics definition. So for example, their theory is only defined, it's only defined if the space-time is has no curvature. So like it can only be defined on the torus, but not a higher genus Riemann surface.
Okay, well, life goes on, but
right. So
okay,
right.
But then they might be talking about objects which have a modular invariance but don't have an operator algebra.
Yeah, so I don't think there's a clear relation between what they're trying to define as a 2D QFT versus what physics think as a QFT.
Okay.
But let's just say that, you know, by all these inspiration, they make such a statement. And now there are physicists who try to take such a statement seriously and found highly non-trivial evidence in physics for the statement to be true.
Yeah, okay. So it seems empirically that the thing they're calling the class of 1+1 dimensional CFT may be the same thing as the actual thing.
Yeah, but like in their axioms, like what, I don't know what locality is, you know, I don't know that, how do they describe, you know, our full set of observables? I don't know.
Right. Okay. I mean, the reason I ask is exactly because in these conjectural chiral CFTs that Witten talked about, they clearly have partition functions, but clearly don't have operator algebras. So, or don't clearly, or do not clearly have operator algebras. Not that they clearly don't, but that they don't clearly. I mean, that's the whole, kind of the whole issue with those, right?
Yeah. So if you only define, you know, a quantum field theory where the only observable is like, you know, partition function on Riemann surfaces, then there's no, I mean, Witten's conjecture, it's just a physical theory because it satisfies the axioms you want for such partition functions. The content of Witten's conjecture is whether that limited set of observables has a full refinement in terms of like an operator algebra, as you said.
Right.
And I think it's highly non-trivial that somehow, however mathematicians try to define this Euclidean field theory, it also has some, you know, there's no operator algebra there, at least, not clear that there's some, you know, clean mapping to what physics mean by a QFT. Somehow this constraint, if you just take it physically, there just seems to be, I mean, there's no counterexample so far. Yeah.
But bottom line, they have some set of axioms which may be strong enough to be equivalent to the usual axioms of CFT. Okay.
Yeah.
Interesting.
What are some of the non-trivial checks that their definition roughly agrees with what physicists think of as 2D CFTs?
I think the most, I think a striking check is this thing I mentioned before, the consistency of heterotic string theory. So the TMF, this conjecture implies a quantization condition on this constant coefficient, which I think I mentioned. And the quantization on that condition implies the vanishing of global anomalies when you compactify heterotic string theory down to 2D. And more generally, it's proven by Tachikawa and Yamashita that the full TMF machinery implies that heterotic string theory compactify on whatever has no global anomaly because of this. So that's like one highly non-trivial suggestion for this conjecture to be true. And then there are others.
I don't know if you're still talking, but it's on mute now, or we can't hear anything.
Are you still talking in?
Maybe that's the end.
There's a timer on the.
There's an anomaly.
That was it.
Might be temporarily distracted.
See, sometimes I feel like I drone on too much in the conclusions, right? I would like to do it like this, just say the
Ying,
last
are
thing.
you still talking, or
and then
can you hear us? Okay, we can't hear you. Can you switch your slide if you can hear us? Okay, maybe he can't hear us either.
But we seem to be connected still.
Yeah, we're connected. Is he there?
I still hear you guys.
Oh,
Okay.
clever.
So, and we can hear you, Clay. So I don't think it's anything on our end. It might be on Ying's end.
Send a direct message in the chat.
I guess. Okay.
HEAR.
In case he's confused.
Nothing happened. Share.
This is autocorrect here.
And unshare. You have a.
It's because I'm making up words, I guess.
I know.
Share. He's just gone.
Should we?
Where's he giving the talk from?
I don't know.
He was in Minnesota 2 days ago.
Oh, you probably will.
Yeah, but.
Did you set the meeting to last for only an hour or something like that?
Well, I know it's still there, right? Because Clay can hear us. Clay, you can still hear us, right?
Yes, I'm still here.
I think you mentioned that his laptop broke, so he's using his iPad to Zoom. Maybe there's some issue with the iPad connection.
Okay, we'll give it 2 minutes, and then if we don't hear from him.
Let's have an informal meeting for the
Zoom.
Okay.
Okay,
Okay.
so
Sorry. So this slide, I have not talked about this slide at all in the. Is that right?
no.
Okay. Okay. Sorry.
You
Okay, so let me
address-
talk about this slide. So even if you don't fully, follow or remember all these stuff about TMF and Stokes stationary conjecture, here is one implication of the conjecture that I think you can remember, and when you walk away from this talk. So just consider a 2D CFT with slightly more supersymmetry, so 1, 1, and with C right minus C left divisible by 12. So in this case, a well-known invariant is the Witten index, which is just the number of ground states counted with signs. Now, the conjecture states that TMF is a deformation invariant, and the Witten index is also a deformation invariant as long as you preserve 0, 1 supersymmetry. So by logic, there must be a well-defined map from the subset of TMF classes that's realizable for this, theories with 1, 1 supersymmetry to the integers, which is where the Witten index takes value. And so this map has been studied, and the highly non-trivial thing about this map is that it's non-surjective, which means that not every integer is a realizable Witten index when there is gravitational anomaly. The precise condition is on the screen, on the slide here. 24 divides K, which captures the amount of gravitational anomaly, times the Witten index I. And I don't know of a physical derivation of this condition. And I just find it, very shocking that even a simple statements about just the number of ground states counted with signs, such a basic physical thing, a simple looking condition like this that it should satisfy, there's no physical understanding of it as of now.
Is there a geometric explanation for that for the sigma model case?
In the sigma model case,
I mean, you have some target space that's Flabiau or special anomaly of some sort, and this is a statement about cohomology, right?
but the problem is this cannot be a purely geometric statement, because if it's purely just the target space statement, then it should be true whether it's in 2D or 1D, but it's not true in 1D. So somehow it knows that the space-time is 2D.
Yeah, good.
Yeah.
No, but that's the conformal condition to some extent, no? Oh, wait, sorry, does this have to be a CFT for the statement? It doesn't even make sense for it being a CFT, but
the anomaly is RG independent, so I mean, it's a property of whatever is at the infrared end of the flow, right?
Yeah, you can replace CFT. You can replace CFT by QFT and just replace this CR minus C right. Sorry, C right minus C left by whatever your favorite symbol for the gravitational anomaly, the global gravitational anomaly. It goes through.
it feels like it should have been related to index theory on the target manifold. But there's no immediate version of that.
Yeah, I don't know. Like as I said, it somehow has to know that the space, it's a world sheet. It's not just quantum mechanics. And
yeah, because the anomaly factor.
Yeah, so I'm very glad that you all think that this should be something very easily explainable because it looks like it should be, and I just think the more simple you think it is, the more striking it is that somehow we don't know that explanation. So I think this conjecture and relation to TMF is an invitation for physicists to examine, have we missed something very fundamental? Okay, I'm over time by quite a lot, so let me quickly just tell you that the same non-surjectivity statement holds true for this TMF to elliptic genus map, and it implies the claimed condition that 12 in the context of 0,1 theories, that 12 has to divide k times this constant Fourier coefficient in the partition function. And just applying this very simple condition, one can easily rule out Witten's conjecture for most of the majority of k. Yes?
Sorry, I'm confused. Well, you mean no, but how does it relate to Witten's conjecture for bosonic CFT?
So here's so the very trivial insight is that a chiral CFT is essentially a 0,1 supersymmetric theory with trivial right supersymmetry action.
Oh, sorry, the right side is the zero central charge side.
That's right. That's right.
Okay, I understand. Sorry, I thought, yeah.
Yeah, so it's
it
looks wacky. I mean, it's quite wacky.
It's fine.
And it's a statement about all bosonic chiral CFTs, and you can just go and check them.
It's fine.
And I could not find any counterexample.
Let's go back to Clay's question: why the supersymmetry matters at all? It doesn't matter at all here. That's really what you're saying.
So sorry, what doesn't matter?
Supersymmetry doesn't play any obvious role.
I guess I find it surprising that one could so confidently make a conjecture about 0,1 CFTs without having already made a conjecture about 0,0 CFTs. It just seems like even less. Like, is there some point of view for which the 0,0 case is like quote obvious that the deformation is only C left minus C right, that the deformation class is only that? I would be very interested if there was some perspective that made that even that obvious.
No, I don't. I mean, that would be an obvious guess, but I don't know how to argue that.
No, I mean,
So no, I don't.
I think that's, yeah, I think we are very far from understanding that in field theory.
Yeah.
But this is some kind of version of that on steroids.
Well, I don't know. It's like, is n equals 4 super Young Mills the simplest theory or the most complicated theory, right? It's like supersymmetry sometimes just make things simpler, even though naively you might think.
But 0-1 is
getting
almost
more
no
structure.
0-1 is almost nothing, right? You've gained almost nothing with this one.
Right, but that makes it more.
No,
possible
you
because
have the
it's
elliptic
zero
genus.
equals zero.
But that's why I think that you should also know the zero case. Yeah. Okay. Anyway, this is more just like I don't understand the philosophy of this conjecture. But
yeah, so here I'm saying that you know the 0-0 case if it's a chiral CFT, and I think
yeah,
maybe
no, the
chiral
0-0
CFT
case
is-
embeds into this if it's chiral. I get that, but
yeah.
and just to make sure, sorry, I was in the car on the way here before I was only able to ask intermittent questions. Just to make sure I understand, the deformation, the definition of deformation class is what exactly? Did you settle on an answer to that?
It is, so the statement is that it has to include 0,1 preserving RG flows, both up and down. So you,
Meaning I can add arbitrary degrees of freedom with trivial TMF and then add relevant deformations in the SUSY relevant deformations in the product, that kind of thing.
wait, but by adding you mean tensor product,
Yeah,
and by trivial you mean 0, or
whatever
because
the
if it's-
whatever the zero element is, whatever the gap
Okay.
element is. I mean,
then
you
yes,
definitely
yes,
be able to do
that's-
something like that. That's what RG up means, yeah, in this context.
that's right. That's right. That's right. So yeah, so if you multiply by something that has 0 TMF, then the total TMF is 0, and then the statement is that can be gapped. This kind of RG flow, I mean, this kind of RG flow question is investigated in this paper in the middle, this RG flow of S3 sigma model.
Yeah, I know they did it for like one example,
Yeah.
but I mean,
But-
now you're making a claim about all possible examples.
Okay, I'm making a claim that someone else made earlier. I mean, it's again, it's a conjecture with no known counter example and some highly non-trivial checks.
Is there a version of this conjecture if I increase the supersymmetry?
Good question. So if you go to, let's say 0,2, then you automatically have a U1R symmetry, right? So then your elliptic genus is a Jacobi form.
Yeah.
And so there is a version of TMF, equivariant TMF for Jacobi forms, but it turns out that it's not as constraining as this TMF in the sense that this non-surjectivity is very mild. And I've actually sort of investigated this a little bit. So one could ask, whether this TMF thing gives any new constraints on, say, Calabi-Yau sigma models, which has 2-2 supersymmetry. But then it turns out that all these like quantization conditions somehow were automatically satisfied just because you know that you want the elliptic genus, this Jacobi form. Sorry, the elliptic genus is the flavored elliptic genus is a Jacobi form. So you just take something from the space of Jacobi forms and just forget about the U1 and try to look at this quantization condition, and somehow we just found that it's always satisfied. We don't know why. So
what about 1,1?
So for 1,1, let me see. For 1,1, it would be about this Witten index. So one would be asking, it would be asking about deformation classes preserving, where deformations preserve 1,1 supersymmetry instead of 0,1, right? If it just preserves 0,1, then it would still fall into the purview of the original conjecture. Yeah, I'm not sure. I'm not sure if there's a statement about 1,1. This I'm not sure, but it would have to be. I mean, this quantization condition would still have to be true if we believe the 0,1 statement. The question perhaps is, it would be about the deformation, whether it's possible to deform one from between two theories preserving 1,1 supersymmetry. And I don't know if there's a known statement about that.
I guess this is kind of coming back to my probing around where's the bottom of this conjecture, because I feel like from a physics point of view, if you had some idea about what labels all deformation classes of quantum field theories, you should be able in the same breath to say it for increasing supersymmetry or increasing spacetime dimension. If you had any argument about why this was true physically.
Right. Well,
like, is there a conjecture in higher dimensions also? Or is this like just isolated into 0, 1, it sounds like, basically. In 0, 1 and 2D.
In higher dimensions, I'm not aware of a similar conjecture.
I mean, I think the naive version of the conjecture without supersymmetry is that, topological operators and the associated symmetry TFT in one higher dimension, which is like the generalization of the anomaly, is supposed to be the label. But that's just because that's all we discovered so far. Not really because we have any real reason to believe that any two things that agree on that, we could deform them into each other.
I agree, but that's an orthogonal, like global symmetry is it's an orthogonal direction to the supersymmetry, right? Like,
well,
here
not really.
I can also
Supersymmetry is a global symmetry. Supersymmetry is a global symmetry. I feel like you're probably using a version of that for 0, 1.
Okay, what I'm trying to say is just that even in this 0, 1 story, you could introduce a bulk topological order, and you can talk about the covariant TMF for that case. It should certainly be a well-defined thing. It's not really studied mathematically, but I'm just saying that there's a full, like, you could put the two things together. You could have supersymmetry and then some kind of bulk, and then the two together, if you demand your deformation preserves like all the symmetries that you introduce, there should be deformation classes captured by the equivariant version of TMF.
Yeah.
So, but I agree what you're saying. So let's forget about supersymmetry. You're saying that we believe, if you preserve certain symmetry, the deformation classes is like such and such. But we don't. I mean, how do you?
Well, I think it's more like we know that the labels at least include those,
right?
Because those are by definition deformation invariant. But I don't think we have any. At least I don't know any real argument that would suggest that if two theories agree on all those labels, that they could be deformed into each other. Like, start with a theory with no just space-time symmetry and no anomalies of any kind. Like, then the conjecture would be that we can gap it. And that seems like a very, very interesting thing to try to show, but I don't know how to do that.
There are people who believe that. I mean,
there are people who believe it, but there's no even hint of an argument as far as I know. Just like there's no obstruction to gapping it.
well, I mean, when had this set of papers he couldn't get published for many years that finally got published, so that may count as an argument. No, I don't, this isn't meant as a catty comment. I don't understand the papers, but.
I mean, I think somehow from the lattice point of view, this kind of logic is more believable in the sense that like you can just clearly stack with ancillas on the lattice. Like if you have some lattice system and all the symmetries are on site and there's no anomalies, you can just like stack with a bunch of ancillas and clearly write a term that gaps it out. So I think somehow from the lattice point of view, it seems more clear that this is the right thing. But anyway, sorry for the rant. It's very interesting. I'm trying to wrap my head around it.
Mhm, mhm, mhm. Yeah, I mean, I feel like if there's ever some kind of proof, like it would have to be in some very abstract framework. I don't know, like some version of algebraic quantum field theory. But yeah, I don't know.
Too abstract.
Yeah.
What is even a mass gap in algebraic quantum field theory?
We need a version of algebraic quantum field theory where you can actually prove things.
Okay. Okay.
Anyway, you got disconnected for a while, so just if you're close to the end, just keep going to the end. It's fine.
This is the end of the second part. I don't think. Okay. I'm
Okay, well,
just
then maybe-
not going to talk about the third part.
Okay. fair.
So yeah. So let me stop on this slide because I think this condition on the width index is like, if you remember one thing from this talk, this is the thing you should remember, and I think everyone should think about a physical reason for why this should be true.
Before you end, how long is your classification discussion of fermionic CFTs?
It would be at least half an hour if I go through everything. But I can give you like a 2-minute executive summary if you want.
Yeah, that would be good.
You just show the slides, they'll be on the recording. Yeah.
But
Okay,
yeah,
okay,
maybe a 2-minute executive summary is good. It's a good, or 5-minute executive summary.
okay.
The problem is
Okay,
that Saab has to
I'll
go
show-
back home to his new baby as soon as the talk ends. So,
Actually, no, 12. It's 2:30 now, yeah.
oh yeah, we're actually gonna
Okay.
get kicked out in like 1 minute.
Oh,
Okay, so you really have a
Okay.
2 or 3 minute window to do it.
Okay, okay. I'll slide the slides and talk simultaneously. So, okay. So, chiral CFTs, bosonic and fermionic, have been studied a lot, motivated by heterotic string theory, and this is the rough connection. And so it turns out that three groups concurrently was working on classifying chiral CFT, both bosonic and fermionic. And they're essentially sort of two methods. One is bosonization. The other is like considering the bosonic subalgebra. They both have the word boson on it, but it's a bit different. I also write down sort of the highlights of each work compared to the others. So our strategy is basically, given a fermionic theory, you take its product with chiral fermions until the chiral central charge is such that it's bosonizable. So you bosonize it into a bosonic theory with Z2 symmetry. And therefore, this duality map tells you that in order to classify fermionic CFTs, it suffices to classify bosonic CFTs together with their Z2 symmetries. And that's essentially what we did. And we did it up to C = 16 first because we were motivated by heterotic string theory. And second, also because the list of bosonic chiral CFTs up to C = 16 is relatively manageable. But I should mention that the mathematician group actually did this up to C = 24. So this is sort of the result. And it turns out that we didn't discover unknown theories. It turns out that people in the 80s were already super smart and got everything, didn't miss anything. But we're putting this list on a more rigorous sort of classification footing. We also discussed sort of how everything can be tied together by stacking with ARF and bosonization, fermionization. Yeah, so that's the quick summary. And yeah, and this is the outlook slide. So thank you.
Super interesting stuff, Ying. I'd be happy to continue. If you close the Zoom meeting, I kind of want to discuss with him more just to understand.
Sure. I also have to go.